Welcome to Ask and Learn.
All right, guys, we're doing problem number 114 in Chapter 5 of Chemistry Essential Science. So for 3 hydrocarbons that contain four carbons, you see that chart here. You also see their standard enthalpy of formation. For each of these substances, they want us to calculate the molar enthalpy of combustion to CO2 and water. So we're going to get their we're going to write their formulas down. So first we're going to start with C4H6. And we're producing CO2 and H2O. So we have 4 carbons on the left, 4 on the right. We have 6 hydrogens on the left. We got to have 3 waters, and 6 hydrogens on the right. So we have 8 oxygens here, 11 here. So we're going to have 11 over 2 here. So now we're going to look at the delta H value. So remember Hess's law, delta H reaction is equal to delta H of products minus delta H reactants. So delta H of 1 is equal to 2. We're going to take 285.83 3 plus 4 times minus 393.5 minus oxygen's now mid-standard state, so it's delta H is 0, minus 111.9. That means delta H of 1, 3 times 285.83 plus 4 times minus 3.5 minus 111.9. Delta H of combustion for this one, that's going to be minus 2543.39 kilojoules per mole. Now for C4H8. Then we get 4CO2 plus H2O. All these are going to produce 4CO2 because you have to have 4 carbons on the left, and you have to have 4 carbons on the right, just like you have 4 carbons on the left. We have 8 hydrogens on the left, so we're going to have 4 in front of here. That means we have 8 oxygens here, and then we got 4 more over here, so we have to add a 6 in front of here. 6 times 2 is 12. Now we're going to get Hess's law, delta H of 2 is equal to 4 times minus 285.83 plus 4 times minus 393.5 minus 119 plus 1.2. So delta H of 2 is equal to 285.83 plus 4 times minus 393.5 minus 1.2. It's going to equal minus 271 2,718.52 kilojoules per mole. So C4 H10 plus O2 yields 4 CO2 plus H2O. Oh, so there are 10 hydrogen left, 2 on the right, so we have to have 5 here. 5 times 2 is 10. So then we have 8 oxygen here, 5 here, so we have to have 13 over 2 here. So delta H of 3 5 times negative 2, 85.83 plus 4 times minus 3, 93.5 minus negative 124.7. So this is going to be minus 2,878.45 kilojoules per mole. So that's the heat of combustion for each of those reactions. Now they want us to calculate the fuel value in kilojoules per mole for each of these compounds. So we're going to multiply each of these times us. We're going to divide them by the molecular weight. So let's say F1 for fuel value. Fuel value is equal to, I'm just gonna put in absolute numbers. 2,543.39 kilojoules per mole times 1 mole over 54 grams. So F1 2,543.49 divided by 54. 47.1 kilojoules per mole. Sorry, kilojoules per gram. F2, which is going to be equal to 2,718.52 kilojoules per mole times 1 mole over 56 grams. That means F2 is going to equal 48.5 kilojoules per gram. Then we got F3. 2,878.45 kilojoules per mole. Also, that's 1 mole per 58 grams. 2878.45 divided by 58. That's 49.6 kilojoules per gram. Now they want for each hydrocarbon term the percentage of hydrogen by mass. So we can do that pretty easily. So we would divide the mass of the hydrogen by the mass of the entire formula. So that means F1 is equal to, we have 6 hydrogens here, so 6 divided by 54 times 100. So F1 is equal to 11.1%. So F2 is going to be 8 divided by 56 times 100%. F2 it's going to be 14.3%. Now F3 is going to be 10 divided by 58. So F3 is going to equal 17.2%. Now, for part D, they want us to figure out, by comparing the answers for parts B and C, propose relationship between hydrogen content and fuel value in hydrocarbons. So you can see a pretty linear relationship. As the percent of hydrogen increases, your fuel value increases, and that's to be that's to be expected, because this has to do with the fact that CH bonds, those are actually very high energy bonds. So the more CH bonds you have, the more energy you're going to produce for your hydrocarbon. So the higher your hydrogen content, the higher your fuel value.